So being the life of a fire geek, you know, you're always looking for cool stuff that's kind of interesting. So this is my cool thing of the day. The beavers affect wildfires. And there's this image. Can you see this?
Yeah.
Okay, so check it out. This is how it works. Beavers dam up streams. They create areas of higher live fuel moisture, which is a major regulator of fire behavior. And you can see in this image, the entire landscape around except for the area where the beaver pond has been pretty severely burned. And so 3 cheers for beavers, right? We have to find some interesting stuff wherever we can. Okay, all right, now I'll get back on script, sorry for that. I want to talk about some general issues in fire science, and I thought that it would make sense to use the Santa Catalina's Bighorn Fire as kind of a case study. And as you all know, the thing about ecology is that every place is different, and in fire, we understand that every fire is different. So there's a limit to how much you can generalize, but at the same time, a lot of what we really need to think about was present in our own Sky Islands and in this event that happened last year. So I'm going to use the Bighorn Fire as kind of more of a jumping off point for my discussion. And again, please feel free to ask questions. So taking this as a case study, we can ask 3 kinds of questions. And I should just also say at the beginning that this is all really kind of a setup for Luke to talk about the more fundamental processes of soil and water. And together, between the 2 of us, hopefully you get kind of the whole picture. So we can ask, why did the Bighorn Fire get so large and severe? Was this a climate change fire? That's a thing now. And your comment, John Abatsoglu, about the increasing length of the fire season is an example of that. And perhaps most importantly, from an ecological point of view, are Sky Island ecosystems resilient to fire now and in the future? So these are the 3 main themes that I'm going to cover. And again, please feel free to ask questions. I teach a semester-long course in Introduction to Wildland Fire, 45 lectures, an hour long. So you could imagine that we're going to just touch on some of these fairly lightly. So let's start with how the Bighorn Fire initiated. It was multiple lightning strikes on the 5th of June last year on Push Ridge, north of McCanyon. And for about the first 10 days, it was just really a foothills fire burning, as you can see, thorn scrub, desert grassland transitions, some oak juniper woodland. In other words, fuel types that generally we do not associate with extreme fire behavior. And so on the face of it, you might say, fine, just let it happen. And in fact, in 2015, if you recall, there was a fire on the Finger Rock around on the front of the Catalinas at around the same time of year and burning in around the same type of vegetation. And it never really became a particularly destructive fire. So these 2 events illustrate one of the properties of wildfire, which is its stochastic nature. Seemingly similar ignition points can actually have very, very different outcomes. So one of the ways that we can inform our thinking about how fire moves is what's called a progression map, which you see here. And a progression map simply takes all the dates from when the ignition happened until the fire, usually until it's considered contained. And by the way, contained means that the perimeter is essentially complete. There may be still combustion happening within the perimeter, but the fire is not expected to grow in area. That's what we mean by containment. And the progression map shows the daily progression of a fire event, such as the Bighorn. And they're especially useful for identifying what we call wind-driven spread events. And much of the Bighorn Fire was wind-driven. And this is a property of large fires, very common, that'll have a series of wind-driven days. I'm sorry, is somebody trying to ask a question? I'm hearing a voice. Okay. So the remarkable thing about the Bighorn was that after the 17th of June, there was a dozen days of 5,000 acres or larger in a row. That is a lot of very, very, very large fire spread. And you can see, you can make out the colors here. You can see, for example, everything in one color, this one polygon, that's one day. Here's another day. You can see some of these days were very, very large in contrast to the early days when it really hadn't started to grow very much. A typical progression for a big fire like this is to have a few days of kind of slow buildup, then it really blows up, often in association with wind, and then it dies down again and has a kind of long tail of fire spread. So that's a very typical progression for a large fire. So June 17th, when it took off, 12,000 acres that day. Now remember, the Santa Catalina's being a sky island are not a gigantic area. So a 12,000 acre day, that's pretty big. Why did that happen? Well, we had sustained winds, high winds, but the gusts were really very significant, 45-mile-an-hour gusts, very high temperatures and single-digit humidity. And there's actually an index of fire behavior that's been constructed called the hot, dry, windy index. And you combine those factors with different weighting, different coefficients, and you get a pretty good predictor of what would cause fire to spread. But of those three, I have to say, it can be hot and dry, but if you don't have the wind, you're not going to get a big event. Wind plays a key role in the spread of these events. And as I said, it grew 5,000 to 9,000 acres every day but one for almost the next 2 weeks. So that's the point at which the fire transitioned across the entire elevation range of the Catalinas. And here you see another characteristic, that it began in a fuel type that generally does not support extreme fire behavior, because fire needs mass, fuel mass, which is really stored energy. And in a lot of the lower elevation fuel types, you just don't have the energy stored to support the kind of behavior that you see here. So why did the Bighorn fire get so large then? Well, we often refer in fire science to something called the fire behavior triangle: weather, topography, and fuels. And generally, these are all in play to some extent. And we certainly saw that in the Bighorn fire. Topography have steep southwest-facing canyons, which accelerate fire behavior because they're directly facing into the afternoon sun, when temperatures are highest, relative humidity is lowest, and it's getting that full-on afternoon sunlight. Fire also moves much faster uphill in steep terrain. Burning materials can be thrown across these canyons to start a spot fire on the other side of a canyon. And especially, it's extremely difficult and dangerous for firefighters to operate in those areas. So we had all the elements for topography to contribute to a big fire. Fuels, if you remember, spring of 2020, we actually had some late season precipitation, which promoted the growth of fine fuels. And fine fuels are important because in almost any fire, it's the fine fuels that carry fire behavior. You can have big fat tree trunks and large fallen trees on the ground, big dead snags. Those are not what carry fire behavior. Fire behavior is carried by grasses, forbs, that is non-grass herbaceous plants. And a canopy fire is really just burning the leaves of the trees, not the stems, not the big branches, it's burning leaves. And when you think of it that way, it's quite remarkable that this amazing fire behavior is all coming from the burning of very, very small fuels. And then, as we've already said, you had this combination of high temperatures, very low humidity, gusty winds, and those would be what would promote the days of large fire spread. So the other factor going on, of course, was fire suppression. I'm sure any of you who were here at the time, you saw the air show shown here. These tankers are dropping fire retardant ahead of the fire spread. There's no point in dropping retardant on a massive flaming front. It's just going to evaporate. neither is there any point in dropping it behind the flaming front because that's in what's called the black, and it's already combusted the fine fuels that are going to carry fire behavior. So you drop, the pilots attempt to drop retardant ahead of the fire and hope that it'll still be there when the fire gets there. This is an extremely difficult and dangerous task. You can imagine the turbulent winds that surround the flaming front in a big fire. So it's hard enough to fly, let alone drop the retardant so that it falls where you want it. And in addition to the air show, there's that on the ground suppression, which we talked about, the firefighting. And increasingly, since 1994, a major event in Colorado, when more than a dozen firefighters, both men and women, lost their lives. And then again in 2013, the Yarnell Hill fire, when 13 firefighters lost their lives. Agencies are increasingly reluctant to put firefighter lives at risk to save somebody's summer cottage. In fact, they pretty much won't do that anymore, which in my view is a good thing. And so that means that there's a limit to how much on the ground firefighting you're actually going to see in an event like this. I called it the air show. Everybody, members of Congress, want to see this. It looks like you're trying to do something. The sad fact is that this rarely influences a major fire like the Bighorn. It's kind of showing that you're trying to do something, but usually what puts out big fires is weather. The weather eventually dies down, or the monsoon happens, or if it's burning in the summer, the fall rains come, or it just runs out of fuel and runs up against a topographic barrier. It's not to say that retardant can't guide the progression to some extent, but major fires burning under extreme conditions are not put out by retardant. And this stuff is expensive, hundreds of thousands of dollars an hour to do this kind of activity. Okay, so now the fire's over, the TV crews have all gone home, and now we're left with this landscape. And this is when Luke and I show up, kind of ambulance chasers, and because we're interested in how these ecosystems recover a variety of processes after the fire. So to understand that, the key concept here is what's called fire severity. And let's make the distinction between fire severity and fire intensity. Fire intensity is the heat output during combustion. It's the amount of energy that's being liberated by breaking the molecular bonds in all those fuels. That's heat fire intensity. Fire severity is an ecological effect, typically on soils and or vegetation. And this can be assessed a wide range of ways, from people on the ground, literally walking around in the fire. These days, more often, especially in a big event, we use satellite data that can detect the presence or absence of chlorophyll and water and use that to construct an index that is a pretty good, at this point, a pretty reliable estimator of how much vegetation has been damaged and what the damage has been to soils. And Luke may talk more about this from a soil perspective. So this is a fire severity map burned when the fire was actually contained but still burning. And you can see that this large area, oops, lost my cursor. Can you all see my cursor when I'm moving it around? Okay, hope that's a yes. So here's Summerhaven right here. You can see the fairly heroic efforts. There's the road, and able to protect Summerhaven. The biggest fire effects, most severe fire effects, were just to the north of that. And that's burning in mixed conifer forest, ponderosa pine, and Madrean pine oak, which are the three areas that Luke and I and Ann McGuire and Craig Rasmussen and some other colleagues and students are most interested in, where the effects were most significant. It's also worth saying, reminding ourselves, that the Bighorn Fire burned areas that had been burned in many previous fires. In fact, when you look up at the Catalinas, or you look up, in fact, at any forest in Arizona, you have to remind yourself that every forest is post-fire. There's no such thing as a non-forest fire forest in pretty much the entire Western US, with the possible exception of the the wet forests on the coast of Oregon and Washington. But even those have fire return intervals. They're just return intervals in the scale of hundreds to thousands of years. The Santa Catalinas would be the kind of forest that would have fire every 2 to 10 years, mostly low severity surface fires. But these used to be very, very large events, sometimes covering the entire mountain range. What we've mapped here are just the fires that have occurred in the Catalinas since 2000. And you can see there's been about half a dozen of them. And these include not only the big fires like the Bullock Fire in 2002 and Aspen Fire in 2003, but also some smaller fire events. And so what the Bighorn Fire was largely doing was reburning areas that had been previously burned. Now, remember when we were talking about that containment, and I pointed out, I think that there could be areas that are unburned within that perimeter, and that definitely is the case here. So these are not necessarily always the second burn. Sometimes it was within the perimeter of an earlier fire, but a patch that happened not to burn. So there are many, many different combinations of burning and reburning. But this is just to remind ourselves that just during this 20-year period, there's been a lot of fire activity in the Catalinas. This then sets up the topic that I believe Luke is going to cover, which is post-fire flooding and erosion and the whole water side of that. And I'll just say this in passing, that this is, of course, also very consequential for the recovery of the vegetation, because if you have massive topsoil loss and severe erosion, it's going to take that much longer for the vegetation to recover.
Don, if I can interrupt.
Please.
I have a question from Dan, and this was actually something that I had jotted down to ask. What kind of chemicals are used in the retardants, and what are the environmental impacts? He remembers that the retardant lines were visible on the Catalinas long after the fire was over.
Right.
Yeah, it was quite picturesque.
Yeah. If you want to look at it that way. Well, yeah, kind of lipstick pink, right? And of course, so what you're seeing is a dye that's in the retardant, so that the pilot can see where it's been dropped. And by the way, it's really important that they have to coordinate with the ground crews, because this is hundreds of thousands of gallons of water and being dropped, and people are injured and sometimes even killed by being right under the drop. So they have to be very careful to coordinate their drop. Now, remember I said that they usually drop the retardant ahead of the front. Firefighters would usually not be right ahead of the front. That's a dangerous place to be. They would be back from it or in the black. So, but it still requires coordination. In addition to water, there's a range of nitrogenous and phosphate containing compounds that help give it more retardant capacity than water. Basically, the retardant is trying to deprive the fire of oxygen. So I showed you the fire behavior triangle, but there's a more fundamental triangle in fire science called the combustion triangle, which is literally the triangle of elements you need to have an oxidative reaction. You need fuel, you need initiation energy, and you need oxygen. And the way that all fire suppression works everywhere is to deprive a fire of one of those three legs of the combustion triangle. So the nitrogenous and phosphorus containing compounds in a retardant essentially soak up the oxygen, if you want to think it that way, and make it more difficult for the fire to progress, as well as the moisture, which absorbs heat. There's been a lot of work on the ecological effects of fire retardant. They've gotten better. They are less noxious than they used to be. In general, they are prohibited from dropping them into riparian areas or into open water because they're definitely not healthy for aquatic organisms. And in theory, they're supposed to minimize the use of retardant, but as I said, the public and members of Congress want to see that the agencies are doing something, right? Well, what you can do that you can see from the comfort of your house down in the valley is that there are airplanes flying around dropping retardant. So was this a climate change fire? And I hope I answered that question. I'd be happy to return to it later. Well, historically, June is the peak fire month for the amount of area burned in our area. You can see this map here. Sorry about that, I'm outside. I'm just going to pretend that that car alarm is not going off. If that gets really annoying, I'll move inside. You can see we've got several areas of the United States marked out here. A is the Mogollon Rim and the Arizona Sky Islands, and that's this panel right here. And you can see that the black bars, which are area burned, actually peaks in the 6th month, that is June. The number of fires, though, peaks later in July and August, and that's after the monsoon. So why is that? Well, June is the period when, as we all know, we have high temperatures, low humidity, long days, and dry lightning. Perfect recipe for a fire to start. But the number of fires peaks in the monsoon because we have all that lightning ignition. It's just that fires that initiate during the monsoon don't tend to spread. You get lots of fires, but they tend to be smaller. And so the period of time that we look for the largest fires is May and June. So from the point of view of seasonality, we would not say that this was an unusual time of year to have an event. Can I just ask if that car alarm is bothering all of you? Because if so, I can move inside.
Doing okay here.
What's that?
Not a bother here.
It's not bothering you? Okay. All right. Glad to hear it. Because it's very distracting to me sitting on my porch.
It's definitely
okay.
audible.
What's that?
It is definitely audible, but we can hear you.
Yeah, I'll move inside. All right. Sorry. Just I'm going to turn my camera off 1 sec. I don't know, but sorry about that.
When you do start up again, we've got a question of whether fires cause climate change.
Yes. Okay.
So
If I can put a pin,
appropriate point.
yes, that's a great point. If I can put a pin in that question and come back to that later on. Okay. So was it a climate change fire in terms of its seasonality? I would say no. May and June especially June is our peak month for area burns. So that from that respect, it was not unusual. On the other hand, we've done some work looking at the effect of seasonal climate on area burned. And we found that the interior West, in the middle of a multi-decadal drought, as you can see in the upper panel, leads to really big increases in potential area burned. This is a modeling study published about 4 years ago. And what we put into this were snowpack, winter, spring, and summer climate, and the effects of the longer fire season. And what we get is a very, very strong signal that seasonal temperature variation does make the fire season longer. And so you would superimpose that on the rising temperature trend, and the answer you get then is that fire seasons are going to get longer, as John Abatsoglu's comment reinforces. And this is going to lead to much larger area burned throughout much of North America. We published this paper in 2017, and sometimes, all I can say is sometimes you hate to be right, but this is one of them. It's been, unfortunately, we've been seeing exactly these areas where area burned is increasing. Okay, so let me pivot now to my last section before I hand over to Luke, and that is fire effects, the ecology of studying fire. We tend to separate this into two general categories. First order or immediate fire effects, which are things that happen during the actual process of combustion. That can include soil damage, killing plants, Parenthetically, animal mortality is generally very low in most large fires, especially among birds and larger mammals that can get out of the way. There's some mortality in soil dwelling smaller mammals, but even that is generally not that great. So we go out and we study as soon as soon after the fires we can get there, these first order effects. And then the second order effects are the effects that can last for many years. And this is, I think, where the work that Luke and Dr. Uberg do that show the hydrologic after effects of a fire, which can be years and decades. And these second order effects, you would think second order would mean they're less important. Those can be often much more consequential and lethal. There have been years when the majority of fatalities, civilian fatalities from wildfires, all happened after the fire was out. It all happened because of post-fire flooding, debris flows, and things that I'm sure Luke is going to cover. So this leads us then to ask, will the Catalinas be resilient? And I think there's good arguments to be made on both sides. On one hand, we know that our ecosystems and the biota that live here are very definitely fire adapted. Fire has been here for a long time. It's shaped species evolution for millions of years. It's shaped the distribution of ecological communities in the Southwest for 10,000 years at least. And even after a big fire like the Bighorn, there are lots of species that are ready to move in. I've listed some of them here. These are species that you'll now see in great abundance up in the Catalinas. So they're doing fine. They're natives. They're fulfilling their ecological role, and that is one form of resilience. On the other hand, the prolonged drought that we are in, and we're still calling it a prolonged drought, although pretty soon we would just be calling it a new climate normal, is very, very challenging, especially for seedlings that do not have the resources to tough out a bad year. Extreme fire effects we're seeing in some cases, both to soils and vegetation, that can really delay recovery for a very long time. And then decadal changes in climate would influence both how fire burns, but also how vegetation grows and what's going to be suitable. So here are some pictures from the Catalinas, and these are taken not long after the fire went out. So you see this kind of burned hillside, a lot of some dead vegetation in the front. You can still see the vegetation in the back that was killed, but it's still present. And so this is a vulnerable time when heavy rains might cause a lot of erosion. After the Aspen fire, we actually got lucky. There was not terrible erosion post Aspen fire in some parts of the mountain. And that's partly because they regrew so quickly with some of these early post-fire colonizers like ceanothus and aspen. You can see this whole back hill slope was forested, but it's very quickly been covered by post-fire shrub growth. And these are native shrubs that help to stabilize the soil. If you go up on Mount Lemmon today, you'll also see a lot of this bracken fern, Pteridium aquilinum. It's pretty much a circumpolar fern. And not only is the brightest green thing you're going to see up there at this scale, but it also plays this role of helping to stabilize soil. Its leaves dry and senesce and fall at the end of the season. That helps to create a layer of litter, which protects the soil from erosion. So seeing a field of this like bracken fern is not all bad. And by the way, you notice there's spaces in here, which make some room for tree seedlings to actually colonize. So we look for this transition from mortality to recruitment, and this is our process of recovery. And we're always asking then, what regulates this recovery? So here's just a few images of what post-fire recovery looks like. Here's a site up in New Mexico, 2 years after a pretty severe, I'm standing on the edge of a pretty severe fire patch. And we counted 100,000 stems per hectare. That's 2.5 acres. In fact, upwards of 150,000 stems per hectare. That's way above the number of trees you would ever have. So you can see prolific seed production. We often sometimes see this wave front of reproduction. You can see how the trees in this burned area are all coming from the seed source in the background. And they're moving out kind of like a wave, and there'll be successive waves as these trees regenerate. So the things we look at in post-fire ecology, is there a seed source? And can the seeds get there? Is the climate suitable for seedlings to survive and establish? What's the pool of species available? Are some of these early successional plants as well as the late successional plants? Because you really want to have both in order for the ecosystem to recover quickly. There's also a chance in this. Whose seeds happen to get dispersed, who gets there first and gets established, and then of course the below ground resources that are so critical. So I'm going to hand off to Luke at this point, and then if it's okay, when we have discussion, we could come back to the question of how fire accelerates or what role it's playing in climate change itself.
Okay, I'm going to mention one other question, which maybe you'll want to also hold. How has the fire affected the spread of buffalo grass?
Great. Okay, good. Good. Okay, well, let's definitely return to those 2 points.
Okay. Well, thank
Thank
you. This was, we learned a lot and have a good sense of what's going on now up in our Catalinas. I'll introduce our other speaker, Luke McGuire. He's an assistant professor in the Department of Geosciences at the University of Arizona. He got his PhD in applied mathematics from the University of Arizona in 2013 and worked as a postdoc researcher with the U.S. Geological Survey Landslide Hazards Group before returning to Tucson in 2016. His research focuses on understanding the role of fire and extreme events on erosion and geologic hazards, including flash floods and debris flows. Certainly things that we think about when we think about fires in the Catalinas. So thank you, Luke.
All right, well, thank you so much for the opportunity to have this conversation today. And like Don, of course, I want to emphasize that I welcome questions and look forward to what you all would like to discuss after this. So feel free to ask questions during or after, obviously, too. So let me share my screen here. And thank you, Don, for the fantastic setup for this segment. Because as you mentioned, I'd like to talk about some of the effects after a fire, and in particular, the hydrologic effects and hazards that we often face. What this has been called in the past is something referred to as the fire and flood sequence. And that's just, comes out of observations that people have made in all types of fire-prone landscapes around the world, that potentially dangerous floods often follow wildfires as a result of how the fire affects the vegetation and the soil. And so I'm going to describe a little bit about that. And I also tacked on here the title to this, the fire, flood, and debris flow sequence. And so I'm going to talk about debris flows and what they are, how they're different from floods, and how we should consider their impact when we think about sustainability and the built environment in kind of this new fire regime that we're beginning to experience. Don mentioned Ann Uberg earlier, who's the researcher with the Arizona Geological Survey. I couldn't have done a lot of this work without her, so I absolutely need to acknowledge her and a variety of other collaborators here at the U.S. Geological Survey and various graduate students and postdocs that have worked with me over the years that have helped us learn a lot more about fires, floods, and debris flows in Arizona. And so a couple of things that I'm hoping to touch on today are, like I mentioned, what are post-fire debris flows, what areas are susceptible to them, and why should we care about them? And perhaps most importantly, how can we assess the potential for debris flow impacts and hazards before a fire starts so that we can consider them as we're making decisions about, maybe things as simple as where we want to put infrastructure. This isn't a new problem. These are some photos on the right from Southern California in 1934. This is actually an area that today is suburbs of Los Angeles. It wasn't as densely populated then. In the background are the San Gabriel Mountains. And you can see, just based on how far off we are, how far off the mountains are in the distance, we're several miles off the mountain front, yet there's massive sedimentation, large boulders everywhere covering the street, partially burying these houses, partially burying a car. This was a result of a rainstorm that followed a fire in 1934. So we've been experiencing these types of events for some time, but they're just becoming more and more common, and we have to deal with them more as we tend to build more in fire-prone areas. So there's a couple of things that I want to get out of the way first, a few definitions, because you're going to hear me talk about floods and debris flows, and I want you to have a mental image in your mind when I talk about them. And I hope by the end of this, you'll appreciate some of why the difference among these things is somewhat important as we think about how hazardous they can be. We're probably all somewhat familiar living in the Southwest with flash floods, and these are mostly, mostly consist of water. There can be some sediment in them after fires. They often look black because there's ash in the water. But they're different from debris flows in that they have much lower sediment concentrations. Debris flows are on the other extreme, where you can see here on the right, this channel that's completely filled with this really, really muddy, viscous water that has these boulders in it. This is the mental image I want you to have when you think of a debris flow. And then there's other things in between that we have fancy names for. We call them hyper-concentrated flows because they have more sediment than a flood, but not as much sediment as a debris flow. Let me show you what is fairly typical of post-fire flows and why they're challenging to predict. They can span across these three types of flows. We may get all of these types of flows even in the same storm, where a storm might initially produce a flash flood that transitions to a hyper-concentrated flow that transitions to a debris flow and then back to a flood again. And that makes it very challenging to predict what's going to happen. Where is the water going to go? Where is the sediment going to go? Who is potentially at risk? So here's some time-lapse photos of a hunting camera that we had set up in a small watershed that burned in New Mexico in 2018. What you're going to see are photos that were taken by this camera every minute. And you might not guess it from what you're looking at now, but there's going to be a lot of water and debris moving past here in a second. There's obviously normally no flow in this area, but as a result of the fire, the hydrology has changed. So we get kind of a typical intense monsoon storm, and very shortly after it starts, this flow ramps up and very quickly becomes something that you wouldn't want to be downstream of. And this is typical. That we get very drastic changes in how much sediment is in these flows over very short time periods. Why do I emphasize the difference so much between a flood and a debris flow? The big reason is that we plan generally for floods. We have the 100-year floodplain, the 10-year floodplain, right? We have some sense maybe of what that means. But when we talk about post-fire flows, they have all the sediment in them, and it changes how they move and how they behave. And one of the things that's particularly important is that debris flows tend to form really large bouldery fronts, like you see here in this diagram in the upper left, where the flow is moving from left to right. These debris flows are kind of consist of a watery tail that pushes this really tall bouldery front. You can see an example of that here. This is an extreme case from Switzerland. This would be a very large debris flow. We don't see them too frequently, but these are house-sized boulders here in this very large channel. And this is an extreme example, but illustrates how debris flows are different from floods. And you can imagine that when debris flows pick up all of these boulders and bring them to the front of the flow, it generates, it's something that can generate large impact forces. It's something that's more likely perhaps to jump out of the banks of a channel, whether or not that's a natural channel or a designed channel that was put there by engineers to convey flow in a particular way. Debris flows mess with that. They mess with all of our equations because they don't behave like water. And here's another example of what these flows can do, where you have a couple of USGS scientists marveling at the fact that this debris flow wedged a 1 meter diameter boulder 2 meters high in between these two trees. Floods can't do that. So that illustrates the power of these debris flows, that they're able to suspend sediment this large. And that can result in certain cases, in very destructive behavior. Here's an example from closer to home, the Superstition Mountains that are east of Phoenix. And you're looking at a Google Earth image here of what this area looked like before a fire. And you're going to see on the upper part of this image what happened after the fire went through. The State Route 88 here is highlighted in red, and below State Route 88, the fire didn't burn, it stopped. The firefighters were able to stop it here at this road, and above the road, it did burn. And you can see here all the black that you're seeing, all the ash. Now there's another Google Earth image of what this area looked like after the first big rainstorm following the fire. So let me toggle back and forth here a couple times. You can see where there was erosion based on where there are all these white streaks across the landscape. And that's because the erosion has exposed boulders and bedrock from underneath the soil that was sitting on, initially sitting on the surface. So before the first storm, after the first storm. And I've highlighted a couple areas here with these yellow arrows that I want to point out how wide these areas are of active erosion and deposition, where the sediment is being reworked by these debris flows. It's these active channels are very wide on the burned side, and on the unburned side, they're very small. Both of these areas received the same amount of rainfall, but the areas that were burned experienced these very large flows with these bouldery fronts that moved outside of their normal channels and widened the area that experiences flow. This isn't a problem when it happens in an area like this that's not populated, but it becomes a problem when we have flows that occur in populated areas. So in the Superstitions, this is what it did. It dumped a bunch of sediment down on State Route 88, and that road is still closed, I think, to this day, because it did so much. These flows did so much damage in so many different places that they have yet to repair the road. But nobody was injured. I don't think any infrastructure was substantially damaged. But that's in contrast to what we get in populated areas where we see this. This is another example from Southern California. The community of Montecito, which is outside of Santa Barbara, experienced a number of post-fire debris flows following the Thomas fire. And they were mapped by a bunch of USGS scientists. All the areas that you see in brown are areas where the debris flows came off of the burned mountain front in the top of this image and inundated this developed alluvial fan. All of the circles show you houses or businesses that were damaged, red indicating complete destruction of whatever structure was there. So you can see that there was a substantial amount of damage done by these flows, and you can see some images of that on the right. So that's what happens when we get these types of flows in populated areas. Why do we see this? Well, fire substantially increases runoff and erosion, and this is due to a couple things. It's due to the fact that, as you can tell in this image on the left, the fire removes a lot of the vegetation, the canopy that kind of shield the surface from the rainfall and helps prevent erosion. And it also, can remove a lot of the litter and duff that you see here on the right that shields the forest floor. So both of those two things are important, and they provide protection for that soil and help soak up some of the water and prevent runoff and prevent erosion. We can also see pretty extreme effects to the soil in some cases. Severe fires can make soil water repellent. And I love this video here on the right. This is one that I made in Southern California. It's me doing an extremely not scientific study of what can happen to soils when they're burned by a fire. I'm taking my water bottle and squirting some water out onto this burned soil, and you'll see that the water just beads up. It doesn't infiltrate into the soil. And it was a little bit windy that day, so you'll see this blob of water kind of vibrate a little bit back and forth. This is extreme water repellency. And this this substantially increases the amount of water that runs off the landscape rather than being absorbed into the soil. As a result of that increase in runoff and the lack of vegetation to help shield the soil from erosion, we see these types of extreme responses where we have here a photo looking at roughly the same area several months apart after a severe fire. You see all of these gullies that are being formed on this steep hill slope and how much sediment has been removed. It's that amount, when you take all of that sediment and you strip it off hill slopes from a large watershed, that's all material that then gets worked into these debris flows, forms those bouldery fronts, and causes flows to move over bank in areas that they don't normally traverse. As Don mentioned, the effects of fire aren't homogeneous across the landscape. Fires burn different parts of the burn area in different ways. When we talk about burn severity, you can see some of the differences here. These are some photos from a fire in Mexico. I just put this in here to point out that every part of a burn scar is different. We don't see the same effects everywhere. And so when we think about hazards and flood and debris flows, we have to take into account the fact that there are these variations, and we have to map them and or try to predict where they are or where they're going to be. That's part of assessing where flood and debris flow hazards are going to be potentially most impactful. And in addition to wanting to try to narrow down areas that are going to be most likely to experience debris flows based on burn severity and other properties, we also need to consider how big these flows are going to be. They vary greatly in size from 100,000 cubic meter flows, like you see here in this photo from Southern California, where this flow is large enough to inundate a fairly substantial area. And you can tell how deep the flow is up against some of these houses, in some cases almost completely covering the houses up to the roofs. Then we can go to the superstitions, and we're looking at smaller watersheds that have less soil available to erode, and we get debris flows that are impactful but much smaller, orders of magnitude smaller. And so yeah, they inundate roadways and cause damage, but they're not doing this much damage. So we need to try to predict which of these two is going to happen. Are we going to get this massive flow or these smaller flows? And I just want to give you some sense of how, as Earth surface scientists, how we go about doing that. There's a couple factors that we tend to consider, and four in particular tend to be most important. I've put them here. One is the topography. So when you think about the Catalina Mountains and you look up at them, there's parts of the mountains that are extremely steep, other parts that are less so. And that's extremely important in determining how worried you should be about these types of post-fire hazards. If a landscape is really steep, you're more likely to see extreme erosion and debris flows that might be dangerous. The other aspect of that is burn severity. If a lot of the vegetation has been removed and there are those extremely water repellent soils that are more common in higher burn severity areas, then you're more likely to get debris flows, and they're more likely to be fairly large. Soil erodibility also plays a role. Some types of soil are just more erodible than others. And then a big thing is the intensity and duration of rainfall. We found that extremely intense periods of rainfall, even if they're short-lived, are often what promotes extreme debris flow activity and dangerous flash floods, rather than long duration rainfall that's less intense. So think monsoon storms. Those are short, intense rainstorms. That's a recipe for debris flows if they impact areas that are steep and burned at high severity. This is an example of a product that we can create from taking into account all these various factors. We can create maps, and specifically when I say we, now I'm talking about not myself, but the community, and in particular the US Geological Survey produces these types of hazard assessment maps, where the yellows here indicate watersheds that have a low susceptibility to debris flows. What you're looking at is the Catalina Mountains and the big scar from the Bighorn Fire. And then the really deep reds here indicate areas where there's a high likelihood of having large debris flows. So we can generate maps like this that tell us where we should expect these hazards. Now, when I think about sustainability, this isn't, I'm not an expert in the built environment. I'm not an engineer. I don't understand how to design mitigation structures. But when I think as somebody who tries to understand debris flow hazards and erosion and runoff, when I think about sustainability, I think about giving those people what they need in order to make decisions to design things appropriately. And one thing that we're starting to be able to do that I think is really exciting is that we can come up with predictions of where post-fire impacts are likely to be most dangerous before a fire occurs. The way that we do that is that we run models to figure out what's the likelihood of a certain part of the landscape being burned. Then if it is burned, what's the likely severity of that fire? Is it likely to be a low severity fire, a moderate severity fire, or a high severity fire? And then I can look at maps of the topography, right, and take into account information about how steep the landscape is, how erodible the soil is, and the likelihood of getting intense rainfall. And we can take all of these factors and put them into these same models that we use after a fire occurs, and we can produce hazard maps that look very similar. So what you're seeing here is a hazard map that was produced by Ann Uberg and some of her colleagues under a scenario where you have a fire, a fairly severe fire that occurs, and the area that they're interested in, you see all these deep reds, meaning this would be a bad scenario. If this landscape were to burn with a moderate to high severity fire, there would be a high likelihood of getting large debris flows out of these watersheds. Here's another scenario where they ran the same modeling exercise, but they made the assumption that the forest was going to be treated before it burned, which would result in lower fuel loads and a fire that wasn't as severe. So you change the severity of your fire, and now you see when you run it through all these models that you get something that's a scenario that's very different. You have only a moderate likelihood of having large debris flows now in these same watersheds. So this gives us an opportunity to kind of play some of these games to see how our actions might affect the potential post-fire, the potential for post-fire hazards. So here's just another example of that. You can go into more detail if you want, of not just looking at what watersheds have the potential to be dangerous, but let's now run models downstream of those watersheds to see if there is a debris flow, if there is a flood, what areas is it going to potentially inundate? And you can generate different kinds of maps like this where I don't want to go into the details, but again, there's just different scenarios, right? For scenario planning of under this circumstance with this type of fire, you're going to get all of the area shown in orange is going to be inundated by a large flood. But over here on the far left, in this scenario where we've done some pre-fire treatments, now we're getting inundation in fewer areas. So there's a number of ways, that I think that people have tried to deal with post-fire hazards. Like I say, that's not my area of expertise, but I wanted to show one thing that I think is interesting. This is how Southern California has dealt with the problem. They've constructed large debris basins at the base of the mountain front. So when the San Gabriel Mountains run right up against the suburbs of Los Angeles. So down on the bottom part of this image here, these are the Los Angeles suburbs. And then where you're seeing all the oranges and yellows here, these are the San Gabriel Mountains. And the color is showing you how many fires have happened in the 20th century. So this is a very fire-prone area. And their way to address the fact that they know they're going to get floods and debris flows when these areas burn is that each of these purple squares are areas where they've constructed a debris basin to catch the sediment that's going to come out of the mountains so it doesn't go into the neighborhoods. They try to catch it all and contain it close to the mountain front. And this is an image of one of those debris basins on the right. And after large storms following fires, they pay a bunch of folks to come in here and get their heavy equipment and excavate all of the sediment out of the debris basin and haul it away somewhere so that the next storm can happen and fill it up again. And they continually empty these debris basins as they fill storm after storm, but it generally prevents impacts downstream. So there are ways that structures and mitigation, that mitigation structures can be constructed if you have a means, maybe using models like this to predict what areas are vulnerable to these hazards and how much sediment you can expect from them. So that's kind of a whirlwind tour of post-fire flood and debris flow hazards. And I hope I've given you some sense of where we're at as a research community in terms of being able to predict and understand these hazards. And that I guess the silver lining is, even though they may happen more frequently in the future, or we may have to deal with them more in the future, is that we are starting to develop tools that we can use to assess the potential for hazards before a fire actually starts. So I think that's maybe one of the more exciting things that's happening in this area of research currently. So with that, just have to also acknowledge, in addition to my collaborators, the various organizations that have funded our work here in Arizona, and leave you with this awesome photo of what debris flows can do in terms of carving out channels and doing lots of erosion. This was a debris flow following a fire in New Mexico, carved this channel out of an area where there previously wasn't one, that after one or two storms is now as deep as this person. So pretty impressive. So I'll end there, and if we have any time, I'm happy to take questions. Thanks.
Luke, I'm going to start off with one question to follow up. Are the hazard maps that you talked about being used in some way here in Southern Arizona?
They are. Yeah, the U.S. Geological Survey produces those hazard maps for any local government agency or state agency or anyone who requests them. They typically will do them, and they're posted online. You can, if you Google USGS post-fire debris flows, their website will probably come up, and you can find hazard maps that look like the one I showed for many fires that have occurred in the Southwest and in Arizona over the years. And they're often used by the burned area emergency response teams that come in after a fire and are tasked with putting into place, coming up with post-fire strategies to mitigate potential hazards on Forest Service land. And Don may be able to answer this better than me about what a burned area emergency response team is tasked with doing. But they're used by folks like that to help make decisions about where they might want to spread mulch to try to prevent erosion, or where they might want to put up some barriers to redirect flow or things like that. So they are used for decision making purposes broadly throughout the Western U.S., I think.
Oh, that's good.
Well, there was the question earlier about how fires relate to climate change. Should I circle back to that? Okay, Stuart says yes. Wildfires intersect the global carbon cycle in two primary ways. First of all, they're burning vegetation. So at least in the short run, they're reducing the photosynthetic capacity of an ecosystem, which means that they reduce to some extent, either large or small, the ability of that system to sequester atmospheric carbon. So that's definitely a factor. And then this is where the question of ecological resilience intersects with the carbon cycle. If the regrowth is rapid, and here we don't necessarily mean individual species, but the total amount of biomass and the total amount of photosynthetic area, then there may just be a little blip in terms of the rate at which that area acts as a carbon sink. But if you have a massively deforested and severely burned area, such as several that Luke showed, effects could be for decades. So an effect on the ability of the system to sequester carbon. And then secondly, during the process of combustion, during the act of burning, a lot of what's being released are greenhouse gases. So if you go back to the last time we had a chemistry class, which some of you may have been just last year, making no assumption. If you remember that you're oxidizing a carbohydrate, you're going to produce CO2 and water primarily. There are other trace molecules that are involved, but if you're burning cellulose, which is just a complex carbohydrate chain, that's 50% of the biomass, woody biomass is cellulose. Another 25% is hemicellulose. So just long carbon chains. You're basically going to be releasing a lot of CO2 if you burn under ideal conditions with plenty of oxygen and the fuel being dry. If you're burning under real conditions, then you get a lot of other products, carbon monoxide, you get nitrogen oxides, sometimes methane is actually generated. There's a wide range of compounds, and many of these are in fact greenhouse gases. If you have incomplete combustion, you're also releasing soot, which is unburned, small particulate unburned material of the size that's about the diameter of the alveoli in your lungs, which is why it can be a health hazard. And so during the act of burning, then you're releasing a lot of greenhouse gases. And the question is does that add up to anything significant? The work that's been done on this suggests that wildfire, broadly speaking, including intentional burning of pastures in Africa and North America, actually all over the world. So not distinguishing between a bighorn fire and the kind of burning that happens in ecosystems every year, is about 5 to 8% of the global carbon budget. So it's not inconsequential, it's adding significantly. In large fire years, it can be even larger. For example, in the years 1997, 1998, there was a very strong El Nino, which in Indonesia and Malaysia is the climate precursor for severe drought and severe fire weather. In those, and the fires in those years released huge amounts of carbon and other greenhouse gases into the atmosphere. And that single event amounted to about 1/4 of the global carbon budget for the year, 1/4. That's just one giant fire in a tropical forest. The fires in the Amazon, which are as much political fires as they are forest fires, those are releasing, probably double the average amount. So there are years when fires are pushing the up to maybe 10% of the global carbon cycle. That would suggest then that wildfire would have a positive reinforcing, a positive feedback cycle. You're burning, you're reducing the ability to sequester carbon, you're actively releasing greenhouse gases. That's going to accelerate climate change. That makes wildfire seasons longer and the temperatures higher, and it's a positive feedback cycle. The only thing that pulls it back from just spiraling out of control, and there's no guarantee that it won't spiral out of control, but the thing is that climate also, in some cases, reduces the productivity of ecosystems, which means you have less to burn. And especially in arid and semi-arid systems, you get into these hot, dry conditions, you're actually producing less fuel. And so that actually can tend to attenuate this fire climate feedback cycle.
Sorry, unmuted. How has we had the question earlier, how has the fire affected the spread of buffalo grass?
Yeah. So here's the thing about fire and grasses generally, they have about a 5 million year long love affair. And fires love grass. They burn enthusiastically through it, and grasses love fire. Fire actually shaped the evolution of grasses. It's the reason that grasses have their growing point, as you probably all know, at or below the ground surface. Whereas woody plants have their growing point up at the apical merostem, or the tip of the branches and the stem. So when fire comes along and top kills a woody plant, unless it has evolved the ability to resprout, it's going to die. Grasses, of course, when they cure, all the vital nutrients are withdrawn back to below ground. The growing tip is right at the surface. So when a fire goes through burning the cured grass blades, it does absolutely nothing, except that it actually helps the grass because it reduces the amount of thatch, which interferes with light transmission. So fire is actually good for grasses. Then you would want to make a distinction between annual and perennial grasses. So the perennial bunch grasses have this below ground merostem, and they generally benefit by better light, recycle of nutrients. Annual grasses are going to be killed, but if they are fire adapted, then their life cycle is actually adapted to, so they've done their reproduction by the time the fire comes along. And this is what buffalo grass does. It's an annual grass from Africa. And when it burns, you're not going to burn buffalo grass out of a system. You're only going to encourage it. And this creates what is called the grass fire regime, or the grass fire cycle, where annual grasses encourage burning, and burning encourages spread of grasses. The place we've seen this most dramatically is in the Great Basin, with the spread of cheatgrass into what was historically the Great Basin sage steppe, which covered hundreds of thousands of square miles in the Great Basin. Much of that has now been invaded by cheatgrass, Bromus tectorum, and that creates a grass fire cycle that kills all the shrubs and basically type converts from a shrub steppe to a grassland. And once you're in that alternative state, then fire will maintain the ecosystem in that altered state. So with buffalo grass, you're not going to get out of it with fire. Fire, in fact, if anything, can make it worse. So the strategy for buffalo grass has to be to eradicate it by other means and try to break that grass fire cycle.
And have we seen considerable spread from recent fires in this immediate area?
So I had a map of the Bighorn Fire and the buffalo grass areas. As it happened, the Bighorn Fire burned through some stands of buffalo grass that had saguaros that suffered pretty severe damage, but it was not the majority of the area that was burning. It's a little easier to control a buffalo grass fire if it's not too thick, although I've been in buffalo grass fires that were pretty impressive. Just because you think you're burning grass, don't get the impression that it's not going to have impressive fire behavior. But combination of firefighting, and then just remember the fire was spreading downhill. That's called a backing fire. And everything about a fire wants to move uphill, other things being equal, unless it's being driven downhill by wind, such as the Thomas fire that Luke showed in Southern California. That was a wind-driven fire spreading downhill at about 70 miles an hour. The Bighorn Fire was not doing that, so it was mostly backing down, and that would tend to give you less severe fire effects. But buffalo grass is definitely a ticking time bomb for saguaros in the Catalina, so no question about that.
Okay, one other question we had, how do you treat an area pre-fire? What materials do you use?
Luke, you want to talk about that?
Sure, and then maybe you can add on, because my knowledge of this is fairly limited. But there's a number of ways that the Forest Service and other land agencies that manage land do treat areas to try to rein in fire effects and fire behavior. And that can be things like prescribed burning. That's one form of what I would call treatment. Other forms are what you would refer to as mechanical treatments. That would be things like trimming trees or piling up excess brush and burning that in a controlled way. It could be forest thinning to reduce the density of particularly dense stands of forest. Those are things that I would refer to as treatments that help reduce the intensity and severity of fires. So I'm sure Don may have more to add on to that.
No, you pass. It's good.
Okay.
Yeah.
All right. Great.
The basic principle is the same as what we said earlier, talking about suppression. You're trying to break that combustion triangle. You can't really stop lightning from happening. You can't really stop there from being oxygen. Of course, when you're putting out a fire, you smother it, you do deprive it of oxygen. But the only pre-treatment you really can do is all about fuels. And as Luke said, you're trying to reduce the mass and spatial continuity of fuel, which makes it harder for the energy of combustion to transfer across space, either as radiation or convection most commonly. And the harder you make that, the greater the distance between the fuels, the less likely it is to get a spreading fire, because a spreading fire is essentially just a big chain reaction. And you're trying to slow down that chain reaction wherever you can.
Good, thank you. Okay, and we have a question from Stephen. What can be done during early to medium recovery years to mitigate future impact?
Luke, you want to talk about the soil mitigation?
Sure. Yeah, I can talk about some. Yeah, from the hydrology, debris flow hazard side, and then maybe you can take that from the ecology side. So yeah, I mean, things that I'm familiar with that folks try to do to mitigate impacts after a fire, as you say, in the kind of early to medium years, in terms of mitigating downstream water-related hazards. Sometimes they'll do aerial mulching. So they'll, from helicopters, they'll drop mulch and straw and whatnot to attempt to cover the soil. Like I mentioned, that the soil just being bare and exposed is what helps facilitate a lot of erosion. And that when that sediment gets worked into the post-fire flows, that greatly accentuates the hazard. So the thinking is, let's do everything we can to minimize the amount of bare soil that's exposed. And so this is one way to do it, is to drop mulch and straw in areas that they're worried about. And then that helps to provide a bit of a barrier to prevent erosion. That can be tricky though, because you can't really drop that on really steep slopes, and it's the really steep slopes that are most vulnerable. And then the mulch and whatever you drop can be eroded away too, and then subsequent storms may still do erosion. And so it's tricky, but that's something that's done. And other things that are done that are more downstream can be things like after the Schultz fire, which I think was 2010 or 2011, 2010 near Flagstaff, is that there were some pretty nasty impacts after the Schultz fire in the first year in terms of downstream flooding. And one of the things that the county did following that is that they had work done to essentially reshape some of the topography on alluvial fans in between a developed area that they were worried about and the burn scar, so that they reworked some of these drainages in such a way that promoted the flow to spread out rather than to focus and channelize and erode down in particular areas. You reshape the topography, generate spreading of flow so that you have a broad floodplain essentially that allows sheet flow or really shallow flow over a large area and promotes infiltration rather than further runoff and erosion. So that's one way. And then I think in addition to that, they constructed some basins to help catch runoff and debris, and again, facilitate infiltration of that excessive runoff. So those are things that can be done if you have the time and the money to implement. Those are a couple examples that immediately come to mind.
The reason I wanted Luke to go first is that in the recovery process, you have to say that the stability and health of the soil environment is primary. If you don't have that, you're not going to have a recovering ecosystem. And so the burned area emergency rehabilitation really focuses on the kinds of things that Luke is describing. If and only if the soil environment is stabilized, then you can think about putting vegetation back. And in most big fires, I would say it's a combination of allowing natural recovery of the system, such as those photos that I showed, that wavefront number of seedlings. Nobody put those there. Those are just natural dispersal of seedlings from that remaining wall of forest. And then a lot of tree planting is done, and try to do that in areas where the soils are reasonably stabilized and where the seedlings and saplings will have a good, well, saplings really is what they plant out, would have a good chance of survival. And beyond that, there's a lot of debate about this very point. In fact, we just submitted a paper today, literally today, on this very point about the balance. It's a tension or it's a balance, depending how you look at it, between kind of intentionally micromanaging the recovery so it goes your way and it happens fast, compared to just creating the conditions in which the system can heal itself, right? And you know, in any big restoration project post-fire, I would say you're doing some of both. You don't micromanage every square centimeter of a landscape, you just can't. On the other hand, there are some things that if you waited around and just let the whole system reach equilibrium, bad stuff could happen, like the kinds of post-fire events, hydrologic events and geomorphic events that Luke is showing. So it's definitely a mix. Of course, once you have vegetation established, there's a feedback to that, to the soil environment, because having plants helps soil development. It's a source of organic input into the soil through litter and duff, helps to stabilize the soil with roots. And so the canopy is intercepting rainfall. Look, I'm just showing you that I've actually been listening to you guys, right? So there is a feedback from the vegetation back to the soil environment. And so it's really best, I think, to think of them as kind of a whole.
Yeah. Stephen, is that sufficient? Do you have any follow-up?
Oh, no, that's good. I'd like to hear those details. That was nice.
Great. Okay. Emma asks, what are your thoughts on more long-term fire suppression past a couple decades, and how it contributed to current fuel loads?
Yeah. So fire suppression, you would think it would be easy. You know, you would say, yes, my God, it's terrible events. They're causing erosion. They're releasing carbon. Have to put them all out. Just let's go all in on suppression. And the problem with that is that you just can't do it. The physics and the amount of money you have, you cannot balance that equation to have a fire-free landscape. But it is true that every year that you don't have a fire, biomass is accumulating. Now it accumulates differently in different regions. In grasslands, biomass doesn't really accumulate that fast, even in the absence of fire, because if those cured foliage doesn't burn off, it's going to decompose. It's thin and it decomposes readily. There's a decomposition curve. So, you know, you're losing about a quarter of the biomass per year. So that's an exponential curve. So it doesn't stay around that long. So you don't get massive buildup of fuels in grass-dominated systems. In woody dominated systems, if don't have fires going through periodically that basically do the work of thinning that Luke was describing, but thinning it with fire, prescribed fire or a natural fire, those woody fuels will stay around, especially in the interior Western US, where it's on the whole a little to the arid side, and so that the rates of decomposition are kind of slow. Now you go up on top of the Sky Islands where you're almost in a different biome in that wetter mixed conifer forest, the rate of decomposition is much faster. So a branch that falls on the ground is going to decompose quickly, and they won't accumulate so quickly. Where they do accumulate fast is in kind of this middle zone, the Madrean pine oak and ponderosa pine, or in California, Jeffrey pine, where you've got plenty of productivity, but the decomposition rate is low. And in those cases, the fuel loads are 1 to 2 orders of magnitude higher than they would have been historically. For example, in New Mexico, ponderosa pine, a typical stand density of mature trees would be maybe 100 to 150 stems per hectare. That plot that I showed you, where we're looking at that post-fire regen, have 10,000 trees per hectare. That is, by the way, about 1 tree per square meter. That's about the limiting density. So fire suppression is really a dilemma, and I don't mean to say that it's easy, because we need to suppress some fires because they put people at risk and they can cause ecological damage. But if that's our only strategy, which it was for many decades, it paints us into the corner we're in now. Notice I'm not really answering the question, or I'm not making the call about which way to go. It's a really complicated question, but probably the answer is, some of both, depending where you are.
Okay, and Emma can always follow up with you if she needs more. Stuart asks, what do you think of fire management practices in the Malpai borderlands? Are there methods of fire acceptance and management worthy of our emulation, or do they really apply only to the grasslands ecology?
Well, so the entire borderlands area used to be very, very active fire zone. We did a paper last couple of years ago on fire history in the borderlands, and we found multiple years when fires were very widespread, not only in the big Sky Islands but in the smaller ones as well. People have been living in the borderlands for thousands of years. The human impact didn't just start when Europeans arrived, and there's plenty of evidence that humans have been contributing to the fire regime of the borderlands for, let's just say, thousands of years. So what we're not sure about is whether that human influence on fire regimes was very localized around where people were living or hunting areas, or whether it was widespread. There's a lot of evidence that what humans would do, in effect, would be to amplify the climate signal in the fire regime. So in a cold, wet year, even if you want to have a fire, you can't. The physics are against you. In a warm, dry year, you may or may not get a fire depending if you have an ignition. But if you're a human, ignition, you can play that role in the fire triangle. You can substitute person with a match for a lightning strike. And so what you essentially do is add ignition, conditions where fires can spread. So I would say there's a lot of evidence that the entire borderlands area has probably been very, very active fire for thousands of years. That's an easy statement to make.
Don has to leave in just a couple of minutes. Are there any further questions for Don?
I only have to go because I have to finish my fire exam, my final exam for my fire students.
Fire exam, right?
Yeah, it's fire exam.
That's the honest deadline. I just had one last question.
Sure.
And it goes to human ignition. How do we reduce this? I know there's no easy answer to that. But how do we get people to not be so careless?
Oh, well, that's easy. It's the same answer as getting people to wear masks and getting vaccinated, and voting and
curing cancer and
curing cancer, doing your homework. Right. It's really problematic. A discouraging number of ignitions are from you wouldn't even call it arson. They're just irresponsible behavior. And I'm sorry if I'm going to gore anybody's ox here, but setting off fireworks in a grassland for your gender reveal party is pretty stupid. And we've had several large fires that were caused by just that. There must be a way to celebrate the gender of your child other than that. If you look in California, the area burned correlates with an R squared of about 0.97 to human population living in the outlying areas, kind of where Luke was showing. The closer people get to these fire-prone forests, the more people have their impact. And I would have to ask also, another answer to your question, Stephen, is let's start taking out roads in some of our wild areas, because the fact is people traveling on foot are not the problem. People traveling in vehicles cause all kinds of havoc, including setting fires, either not taking care of a campfire or doing something intentionally or what have you. But fire ignitions are very highly correlated with roads. And so road closures is actually probably a viable strategy that could be carried out on public lands. I'm saying everything except improving human nature. We'll leave that for another time.
Well, no, the roads is a good one too.
Yeah.
Yeah, I like that. I haven't heard that before. That's a great suggestion.
Yeah, and actually the Coronado National Forest, their new forest plan, which they passed in 2018, I think, if I remember what year it is now, it includes a lot of plans for road decommissioning, and they decommission them and then they restore them, so that ideally you go back 10 or 15 years later, you wouldn't know there had been a road there.
That's great. Don, I will prematurely say thank you so much if you have to run off, but for both of you, in a sense, it's following up on what Stephen just asked and what you were saying. Are there any other policies or practices that you would recommend making sense given the kind of fire regime that we're seeing increasing now?
Oh, you want to go first, Luke, or should I?
Go ahead, Don.
Okay, well, yeah, there's two things that are kind of repeating themes. One is land use. We are not very good at regulating land use in this country because of the deep belief in the prerogative of private property. And so our public lands, as I'm sure you all know, are Swiss cheese perforated with roads and inholdings and utility infrastructure and all kinds of things. So that, and with every passing year, what's called the wildland urban interface, that is the area where people are living, and actually it's no longer called an interface, that kind of implies this relationship. It's more an intermix, it looks like that, is growing. This is a function of affluence, more people have money to build second homes. And ironically, COVID taught us all that we could work remotely. And so I can sit in my cabin in Idaho and be a stockbroker in New York. And so that is probably, that's going to have an unknown effect on the wildland urban interface, but it could cause it to accelerate. And then the other thing is, of course, all roads lead to climate ultimately. And so, you know, if we get serious about reducing emissions and beginning to draw down atmospheric carbon, that will probably be the biggest single factor that we could do that would get the whole system back into its equilibrium.
So I could add just something that's not very exciting at all, but one of the, I don't know that I would really say this is a policy necessarily, but one of the things that I think is often faced by folks in the post-fire hazards community is that it's tough to get the right message out about post-fire hazards and what areas are at risk. And part of that is that distinction, like I was mentioning, between floods, flash floods, mud flows, debris flows, and what are the appropriate terms to use that tell the public there's a new hazard here. It's not just flooding like you may be used to, but there's an elevated risk of these different beasts. And in some areas you say, oh, well, there's a increased potential for debris flows. Sometimes it's not clear that people know what that means necessarily, but in Southern California, if you say mudslide or mud flow, they know what that means because the media uses those terms quite frequently. And that's something that they see down there. And so just proper communication of what hazards are, where they are, where there's the potential for them, and the fact that when you're dealing with post-fire flows, it is different than just a typical monsoon-driven flash flood. That's one of the most important things, I think, is improving our communication systems in that way, which people are definitely trying to, for sure.
I have to tell you though, when I was out with Luke's colleague Ann Uberg in the Chiricahuas looking at a big debris flow that happened after the 2011 fire, and I'm thinking, oh my gosh, this is terrible. What, this is a catastrophe. And Ann, who studies debris flows, she said, this is so cool. This hasn't happened for 5,000 years. She thought it was amazing. So even debris flows have their fan club if they're in the right place.
Fantastic. So there's an educational element that needs to come in to really get across to people what it is, what might that they might hear about.
Yeah, it's just kind of a variation on the theme that we're all struggling with, and that is we live in a limited planet. We can't emit unlimited amount of greenhouse gases. We can't consume unlimited amounts of water or timber. We can't. Did you know that the biomass, you probably all know this, the biomass of livestock is about 5 times the biomass of all humans on Earth. And the biomass, the smallest biomass is wild animals. That's a tiny fraction. Humans are like this, and livestock is much bigger. So, can we support that kind of meat-oriented lifestyle with 9 billion people? These are all different questions that, lead to the same central question of whether we can figure out how to live within our limits. And, the kinds of things that Luke and I are talking about today just sort of illustrate one of the impacts, one of the things that happens when a system gets pushed beyond its limits, at least temporarily.